Hello everyone, welcome back to our channel. In this video, we are going to learn about the logic gates. The logic gates are the basic building blocks of any digital circuits. You can able to consider any computers, microprocessor or any calculators. These logic gates are the basic building blocks for that, where they perform simple logical operations on one or more binary inputs that may be 0 or 1, which produce the single binary output. So the output is also either 0 or 1. So if you have any n number of inputs, like you can consider 2 inputs, 3 inputs, 5 inputs, like that. For the n number of inputs, the logic gates will give only a single output. Each logic gate represents a specific Boolean function such as AND, or not, where this AND perform the multiplication or perform the addition. Not will invert the value which is taken as the input. Like if you consider 0 as the input, the output will be 1. If you consider 1 as the input, the output will be 0. So these are all the foundation for all the digital systems like computers, calculators, and microcontrollers. So there are some types in the logic gates. Let's move with that. Logic gates are classified into 3 main types, which are based on how they function and what kind of circuits you can build with them. So the first one is the basic logic gates, second one is universal logic gates, and the third one is derived or special purpose logic gates. Let's understand one by one. First, the basic logic gates. These basic logic gates are the fundamental building block of all the digital circuits. They perform the simplest Boolean operations. Let's understand what are the basic gates that we can able to see. Basically, we can able to see 3 types of the basic logic gates, that are AND, OR, and NOT gates. The Boolean expression for AND is represented by a single dot, and the function of this AND gate is the output is 1 only when both the inputs are 1. Like if you consider 2 inputs, only when 2 inputs are high, means 1, then only the output will be high. In any case, if either one of the input is 0, then output will be 0. So the output function for the AND gate is y equals a dot b. Next one is OR gate. The Boolean expression for the OR gate is the vertical straight line, where the output is 1 when input is 1. Means if you consider the 2 inputs, if either one of the input among the 2 is 1, then the output is 1. If the 2 inputs are 0, then only the output of the OR gate is 0. So the output function of OR gate is y equals a plus b. Basically, it perform addition operation. NOT gate. The NOT gate symbol is exclamatory, that you can able to see here, where the main operation of this is it inverts the input value. If you have 0 in the input, the output is 1. This is the basic operation of these basic logic gates. Let's understand one by one. First one is the AND gate. This AND gate is a basic logic gate that gives an output high only when all of the inputs are high. If any input is 0, the output will be low, that is 0. So the logic circuit of the AND gate is look like this, where here we can able to see the 2 inputs, that is a and b, and the output is a dot b. The Boolean expression for, or the Boolean function for the AND gate is y equals a dot b. Here truth table. The truth table is basically means the output representation with respect to the inputs. Here we are considering a and b as the inputs. A is first input and b is the second input. Here for the input 0, 0, the output is 0. You can consider 0 multiplied by 0. So the output will be always 0. In all the cases like 0, 0, 0, 1 and 1, 0, if either one of the input is 0, always the output is 0. So if both the inputs are high, means 1, then only the output of the AND gate is high. That you can able to see in this truth table of the AND gate. Let's move with the next gate. The next gate is OR gate. This OR gate is a basic logic gate that gives an output high if one or more inputs are high. So the output is low only when all inputs are 0. So this is the logic circuit of a OR gate. which has two inputs here, and the Boolean expression for OR gate is y equals a plus b. Here you can able to see what are all the outputs that we can able to see with respect to the inputs that are given to OR gate. Here you can able to see the OR gate value. In the case only when both the inputs are 0, then only the output of the OR gate is 0. Expect this condition, all the outputs with respect to the inputs are 1. Let's move to the next gate. The NOT gate is a basic logic gate that inverts or reverses the input. If the input is 1, then the output is 0. If the input is 0, then the output becomes 1. So it performs a logical negation operation, means what you will give, you get the opposite to that. So this is the logic circuit for the NOT gate. You have A as input and Y as the output here. Logical expression for NOT gate is Y equals A bar. Why A bar? Because here we are considering A as the input. So the truth table for the NOT gate is shown here, where if 1 is the input, then output will be 0. If 0 is the input, then output will be 1. There is a special thing called the buffer in the logic circuits. Buffer will not convert the input value. It just give the output which is same as the input. So a buffer is a logic gate that simply outputs the same value as its input. Okay, it doesn't change the logic level, it strengthens or amplifies the signal instead. Okay, this is the logic circuit for the buffer, where you can able to see the bubble in the NOT gate, but in buffer you don't see any bubble in the logic circuit. The bubble indicates the NOT operations or inversion operation. If you don't see any bubble in the circuit, it represents it is not doing the inversion operation. So the Boolean expression for the buffer is y equals a. So you can able to see in the truth table what is the input that is representing as the output. This is a specialty of the buffer. Let's move with the universal gates. The universal logic gates. A universal logic gate is a type of the gate that can be used to construct all the other logic gates like AND gate, OR gate, NOT gate, or any special purpose gate also. These gates we can able to design only by using the logic gates. So if you have only this one type of gate, you can still build an entire computer circuit. That is the speciality of these universal gates. Let's see which are the logic gates. The logic gates which you can able to see in the universal gates are NAND gate and NOR gate. So the Boolean expression for the NAND gate is y equals a dot b whole bar represents NOT of 9. This is the symbolic meaning of a dot b whole bar. So when we go for the NOR gate, we have y equals a plus b whole bar, which represents the NOT of OR gate. The inversion value of the OR gate is the NOR gate. So let's understand one by one. Let's move with the NAND gate. The NAND gate is a universal logic gate that performs the AND operation first and then inverts the result. So it's simply an AND gate followed by a NOT gate. So this is the logic circuit for the NAND gate. It has the AND gate followed by NOT gate. So logical expression is y equals a dot p whole bar. Here we can able to see the truth table. In AND gate we got 1 only when both the inputs are 1. But in NAND gate we get 0 only when both the inputs are high or 1. By this truth table you can able to analyze the output of the NAND gate will become logically low or 0 only when both the inputs are high or 1. Okay. Let's move with the NOR gate. The NOR gate is a universal gate that performs the OR operation first and then inverts the result. So it is simply like OR gate with the NOT gate. So it gives output as high only when all the inputs are low. But in case of OR gate, if both the inputs are 0, then only we get the 0. But in the case of NOR gate, if any of the input is high, then we get output as 0. We get output as high only when both the inputs are 0. This is the logic circuit for the NOR gate. We have the logical expression y equals a plus b whole bar. So in the truth table, you can able to clearly analyze that when A and B, here we are considering A and B are the inputs, when and only both the values of A and B are 0, then only we are getting the output as high, means 1. Expect that condition. If you consider the input values as 0, 1, 1, 0, 1, 1, anything, the output value will remain 0. So we get the output as high only when the entire inputs that are coming to NOR gate are logically 0. Okay. Let's move with the other gates. Derived or special logic gates. We can able to call it as special purpose logic gates also, where this derived or special logic gates are the combination of the basic logic gates that are NAND or NOT, that perform exclusive or equality functions. Mainly we can consider XOR and XNOR operations. These are also sometimes called complex or compound gates. In special purpose gates, we can able to see two types. First one is XOR, which is also called as exclusive OR, and second one is XNOR, which is called as exclusive NOR gate. So the Boolean expression for the XOR gate is y equals a bar b plus a b bar. So what is the meaning of this? The output is 1 when inputs are differ. Means let us consider if you have the two inputs, the output will be 1 only when these two inputs are differ by each other. The logical expression for the XNOR is y equals ab plus a bar b bar. So what is the meaning of this? The output is 1 only when both the inputs are same. Means if you consider two inputs XNOR gate, like A and B are the inputs, when and only the values of A and B are same, then only the output of this XNOR gate is logically high or 1. Let's understand one by one. First, the XOR gate. This XOR gate, also called as the exclusive OR gate, gives a high output only when the inputs are different. In other words, if both the inputs are same, then the output will be 0. If the inputs are different, then output is 1. This is the logical circuit for the XOR gate. Here we are considering A and B as the input and Y as the output. The logical expression is Y equals A XOR B, that is A bar B plus A B bar. Here in the truth table you can able to see, like here we have A and B as the inputs. When and only both the inputs are not matched, means if A is 0, the B should be 1, then only we get the output as 1. Or if A is 1, the B should be 0. On that case only the output is 1. If both the inputs are same, like A is also 0 and B is also 0, the output will become 0. Or if A is 1 and B is also 1, then also the output is 0. Let's move with the next gate. The final gate in the logical gates is XNOR gate. This XNOR gate gives the output as 1 only when both the inputs are same. That may be either both the inputs are 0 or both the inputs are 1. So it is also known as equality detector gate, because it checks if the inputs are equal or not. So this is the logic circuit for the XNOR gate. The logical expression is y equals a bar b bar plus ab. So this is the truth table for the XNOR gate. Here we are considering A and B as the input. Here in the output you can able to see only when both the inputs, that is A and B are the inputs here. If both the inputs of A and B are same, like 0, 0 and 1, 1, then only the output is logically high or 1. If both the inputs are differ, then we get 0 as the output. So this is how the logic gates will operate in any digital circuits that you can able to see in the real world. So let's meet in the next video. Till then, thank you. Bye.